Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RIT 120 Hydraulics. Today we're going to have a discussion about a very important fluid property known as viscosity. Sounds very similar to velocity, but it's something totally different. Viscosity is basically a measurement of the resistance to flow against an established standard. So my example I like to use when I introduce viscosity is these two substances you see right here, honey and water. There's something very obviously different about these two liquids. They're both liquids. They're going to take the shape of whatever container you pour them into. But there's something different about them, okay? Besides one being a colorless, odorless combination of two hydrogens and oxygen, and the other being delicious bee vomit. Honey has a tendency to pour slower than water. And that's because, you already know this, honey is a more viscous substance. It's thicker, it's sluggish. And if you had the same volume of honey and the same volume of water at the same temperature and you inverted the jars over your head, you would get wet before you got sticky, okay? Because the honey is taking a longer time to come out of that jar, okay? So that's what it means by an established standard, is basically you have to come up with an agreed upon means of measuring this. You know, you can easily say, okay, honey is more viscous than water, but that's relative, okay? So you got to come up with a number. So basically there's some units for viscosity, okay? And what's really neat about viscosity, it's using units that are very similar to what I just talked about, time, okay? The units for viscosity is measured in a Sabelt universal seconds, okay? It's called a SUS, Sabelt universal seconds. And the key there is the seconds. You know, honey would have a higher SUS rating because it takes longer time to come out, okay? And that's how it's measured. It really is. That's how it's, I mean, you don't pour it over your head. You take a given volume of a substance, 60 milliliters, and you stick it inside a flask. You heat it to a certain temperature. I think it's 104 degrees Fahrenheit. And there's a hole in the bottom. The hole is of a certain size for every single substance. And what you do is you put the 60 milliliters of whatever substance you want to measure, heat it up to 104 degrees Fahrenheit in a little bath, and then pull the plug and sit there with a stopwatch and see how long it takes to empty 60 milliliters. Okay, so let's say 60 milliliters of honey. It takes just randomly 100 seconds to come out. You know, water, same 60 milliliters, it would probably take 50 seconds to come out. So thereby, honey is a viscous substance, you know, a more viscous substance. So hydraulic fluids that we're going to be using, you know, 150 SUS at 104 degrees Fahrenheit, okay? What that means, we put 60 milliliters of hydraulic fluid into there and then pulled the plug on the bottom, well, heat it up to 104, pulled the plug on the bottom, it took 150 seconds for it to come out. How this is measured, it's a Sabelt viscometer. Okay, so it's just a standardized method of measuring viscosity. So there's another critical property of viscosity that I like to illustrate with a honey and water example. Say, for example, it's a June day 70 degrees out, and you take your water and you pour it out, and you take a measure of how long it took to come out. And then it's a autumn day, it's 50 degrees Fahrenheit. You take that same volume of water and you pour it out, measuring the time. It's pretty close. It takes, let's say, 6 seconds for the first one, and when it's colder, it takes 6.1 seconds, pretty close. And as long as the water's not freezing, it's going to be relatively close. Honey, not so much. That same warm June day, the honey's been sitting out there and it's gotten to a higher temperature. It's going to flow a lot faster than it would on a cold autumn day or a winter day, for that matter. Let's say at 70 degrees, it takes a certain amount of time. At 50 degrees, it takes a lot longer time. And at 40 degrees, it takes a lot longer. Basically the slow as molasses in January. Our example, slow as honey in autumn, okay? So what this illustrates is viscosity changes. Viscosity is a function of temperature. Okay, viscosity changes relative to temperature. And we need a way to measure this, whether a fluid is stable, i.e. at certain temperatures, across a range of temperatures, it's going to have the same viscosity, versus unstable, i.e. if it changes viscosity rapidly or slowly. Okay, so this is what's known as a viscosity index, or VI. Viscosity index. And the way I like to describe the viscosity index, it's a score of stability. So just like you take an RIT 120, you hope that you get 100 on the exam, and not a 0. Okay, basically this is the fluid's score. So if a fluid got a 0 for its score and viscosity index, means it's an unstable fluid. Its viscosity varies widely across a range of temperatures. And a 100 means that fluid's viscosity stays the same across a range of temperatures. And believe it or not, this is seriously how they did it way back when they invented oil. I don't know when. They seriously basically took the worst substance known, which I can't remember what it was, and the best substance known at the time, and scored it a 0 to 100. And now other fluids have been invented since that time. It is possible to actually have a score even better than 100, a viscosity index better than 100. It was best at the time. Okay, so graphically, what we're going to do is, let's say, here's 50 degrees, here's 70 degrees, here's 90 degrees Fahrenheit, and let's say our substance A, is relatively slow moving at 50 degrees Fahrenheit. And it takes 100 seconds for 60 milliliters of it to drain out of that solution at 50 degrees Fahrenheit. Okay? So now, here's a question to you. If the fluid gets thinner, i.e. easier to flow, at 70 degrees Fahrenheit, will the viscosity number go up or down? And again, go back to exactly what I wrote here. Seconds. Think of it in seconds. If it's warmer, it will take less seconds for that same volume to drain. So we would expect it to go down. Similarly, at 90 degrees Fahrenheit, we would expect it to go down, and that's substance A's viscosity profile for varying temperatures. Okay? So now substance B comes along, the new and improved version of substance A. Let's say that its viscosity, let's put numbers here. That's 80, that's 60, that's 40. It's naturally a thinner, easier to flow substance at 50 degrees Fahrenheit. That's where it would be. And its viscosity changes very little as a function of temperature. Get it? Basically, I'm increasing the temperature of substance B versus substance A. I'm still increasing the temperature of substance B, but look at the range of its viscosity. It's a far more stable substance than A. Okay, so who has a better viscosity index? Quite obviously, substance B. It's a smaller range, it's more stable, it's a better substance. Okay, so viscosity index, it's a score of stability. That's the way I like to think about it. Viscosity, the amount of seconds it takes to drain. Okay, so let's do a little quick exercise here. And here's our quick simple exercise. Of these four substances, which has the highest viscosity? Which has the lowest viscosity? And the only reason why I'm using honey as an example because I don't know how to spell molasses. Okay, so highest viscosity. Again, think of seconds. Which substance is going to take the longest to pour out? Bing. Okay, lowest viscosity. Which is going to take the quickest to pour out? Bing. Basically, it's a little bit warmer. It's hydraulic fluid. It's made to flow, and it's warmer. Okay. Typically, there is a positive correlation. Excuse me, a negative correlation. Basically, as you heat up a substance, it's going to get thinner. There are some phase change substances that will get um, harder to flow as you increase it. But for hydraulic oil, basically, the more you heat it up, the easier to flow it gets, thereby viscosity decreases. Okay, that's a good question right there. If you heat up hydraulic fluid, will the viscosity increase or decrease? The answer is it will decrease because it becomes easier to flow. Okay, one thing I want to talk about viscosity too. We talked about viscosity and the value of SUS, stable universal seconds. There are also these things called viscosity viscosity ratings for ISO and for SAE. I want you to be aware, you're just going to basically look them up in a table. Let's say an SAE grade 50. It's not really um, a 50, a substance with a viscosity of 50. What that's saying is that substance has a viscosity from 16.3 to 21.8 stable universal seconds. Okay, so viscosity range. Because we all know, again, for a particular substance, it has a range as you heat it up or cool it down. Okay, cool it down, you're increasing viscosity. Heat it up, decrease viscosity. Okay, so be aware that there are ranges. Let's see, like an ISO grade 100, that's a viscosity range of 90 to 110 stable universal seconds. So be aware, and they're two totally separate things. ISO grade hydraulic fluid versus SAE grade hydraulic fluid. Depends on which your employer is requiring you to use. Okay, the last thing I want to discuss about viscosity is, again, we've already hit upon a key factor, is viscosity changes as a function of temperature. And you need to anticipate that in the design of your system. So let's say you built this imaginary hydraulic system right here, and it's been working fine at your home, and you decide that you're going to pack it up and show your favorite uncle in North Dakota your new hydraulic system. The deal is you show up in North Dakota in January in the middle of a snowstorm, and your favorite uncle wakes you up at 4 in the morning after an extremely cold night, and he says, "Let me see that new hydraulic system you were talking about." Pretty obviously, what's wrong? Everything is extremely cold, including that fluid inside the reservoir. And what is the viscosity of that substance? Well, think of your cold honey. It's extremely hard to flow, and the viscosity is through the roof. And that pump is going to have an extremely hard time to pump that fluid from the system. Okay? So now let's think of the opposite case. So now you're in the Mojave Desert. You're going to show your grandpa your favorite hydraulic system, and it's 140 degrees in the shade, and you're using it all day long. Pretty obviously, that fluid is going to heat up and heat up and heat up and heat up. What is the viscosity now? Well, viscosity, if it's a typical hydraulic fluid, has gone down. It's easier to flow. Viscosity has gone extremely low, and it's easier to flow. One would think that this would be a desirable circumstance. Well, it isn't. And the reason why is because I know we haven't gotten to directional control valves yet. But inside a directional control valve is this thing called a spool that fits inside this passageway that has extremely tight tolerances between the walls and these things called the lands. And these are valleys. And your system has been designed to operate at a certain temperature range, and you've taken it well outside the temperature range in extreme. And previously, that fluid in between the valleys and lands basically the lands separate the two fluid sections, but now your fluid is easier to flow. It can actually leak through these passageways, okay? So you're going to have problems with your directional control valve there being able to stabilize a load, or hold a load in one position, because the viscosity of the fluid has changed. There's nothing wrong, well, nothing different about your system in either circumstances, whether it's cold or whether it's warm. It's the viscosity of the fluid has changed. The fluid has changed its nature, whether it becomes increasingly harder for it to flow, i.e. viscosity is increased because it's colder, and your viscosity has decreased. It's easier to flow when it's hotter. Okay, so the solution maybe in this case is don't take it to those two extreme environments. The other solution to this may be is if you are going to operate this system in North Dakota in January, you may want to get a different type of fluid that has the same viscosity that your earlier fluid did at a certain higher temperature. Same thing goes with the hotter environment. You may require a different type of fluid, okay, for that hotter temperature. So you haven't changed the system at all. You're just basically putting a owner's notice. If you're operating it in extremely cold environments, we recommend this fluid. Hot environments, this fluid, etc., etc. Okay. There's also other ways to do that. Quite obviously, in a hot environment, we want to cool the fluid. So that is a bonus schematic that you guys get to learn today. It's a heat exchanger. Heat exchanger, a cooler. It's this diamond shape, and it's got arrows pointing out. So heat exchanger, also shorthand HX sometimes. Heat exchanger. And I can tell this is a cooler because the arrows are pointing outwards. Whereas a warmer, the arrows are pointing inward. Cooler, warmer. Okay, so you may want to add an offline warmer as a a cold temperature modification for sale of your hydraulic system in North Dakota. You may want to add a cooler inside your system if it's sold in the Mojave Desert. Additionally, with our heat exchanger schematics, you will also see these lines coming into it. For example, a water cooler has basically, this is our hydraulic line. Here's a water substance that is used to cool this particular device. And what I'm thinking of is here is basically, here's a hydraulic fluid. This is the tube in shell heat exchanger. Tube in shell. That's quite literally what it is. Where hot hydraulic fluid enters this thing and cold cooling fluid is flowing through this envelope surrounding it. And now here's a tricky question. If hot hydraulic fluid is coming in this direction, which direction is the cool fluid coming in and out? The answer is opposite direction. Okay, the way to think about this is, here is our passageways, here's our side view. Here's our extremely hot hydraulic fluid right about here, extremely hot as it enters the heat exchanger. It's progressively cooling down. Here's our cooling fluid coming in opposite direction. Our extremely cold fluid right here is still colder than the warm hydraulic fluid. If we continue this direction, our warm cooling fluid is still cooler than the extremely hot hydraulic fluid at this point. So again, this is you have to have that counter flow, okay, in a tube and shell heat exchanger. This is can also be modified in a something known as a baffle plate assembly. Basically, if you press for space, a baffle heat exchanger has hot fluid coming in through the bottom of this corner, cool fluid coming out the other corner, and because imagine the bottom here, flipping it over. Oops, I should redraw this guy. That's my cooling fluid going in. Ultimately, what the baffle is happening here is basically that's a hot layer, that's a cold layer, that's a hot layer, that's a cold layer, hot. Again, going in that counterflow arrangement. Again, so that's a baffle heat exchanger. You'll see these a lot on solar hot water heating systems. So a baffle heat exchanger and a tube and shell heat exchanger. Okay, so again, critical thing to remember about both those heat exchanger, it's got to have a counter flow to that. Okay, a warmer, could take basically just a heater inside that system, an electrical element heating up that system. The other thing too is those filled in arrows that I used right there for the cooler, if that was if that was an empty arrow, basically nothing, it's not filled in, it means there's an air medium, an air cooling medium, a fan. Think about, a radiator. Basically, hot fluid is entering the radiator. Cool fluid's coming out because as your vehicle is moving down the road, cool, bug-filled air is being forced through it. Okay, so that is an air cooling medium versus a water cooling medium if it's filled in. Okay, quick note about the warmer. As we already kind of figured out, if fluid is moving, it's going to get warm. So sometimes rather than going to the expense of putting an electrical heating element inside a reservoir to keep it warm, sometimes, and this is actually quite common in wind turbines, especially in North Dakota, they basically have an automatic circulation function. So basically what there is, there's a temperature sensor out there. It recognizes that the fluid in the reservoir is not circulating and it is getting extremely cold out and the viscosity is progressively increasing, and you need to have that fluid ready at all times in preparation for an emergency event. So what it'll do, it'll just passively circulate that cool hydraulic fluid until it warms up to a certain point. It's not going to any actuator. It's not really doing anything. It's just the pump is running through a little loop. Okay, so sometimes warmer is often substituted for an automatic circulation. Okay, so that's about it for viscosity. Let's move on to a different subject.